A rock sat in the ground for 4 billion years. It was dull, reddish-brown, heavy, and completely unremarkable. Farmers stepped over it. Children kicked it aside. Builders used it to fill gaps in walls. Nobody looked at it twice because it looked like nothing, like dirt pressed hard, like the earth itself. And buried inside that rock was the material that would one day hold up the tallest buildings ever constructed, carry freight trains across continents, form the hull of ships that cross oceans, and eventually get hammered into the very machines that pull us out of poverty. But for most of human history, the rock just sat there. The question is not simply how we eventually found iron. The deeper question, the one that changes how you see every bridge and skyscraper you have ever walked past, is how an ancient person with no chemistry, no periodic table, no university, and no tradition to follow could look at a dull red stone and somehow, through fire and accident and 10,000 failed attempts, pull a metal out of it that Stone Age technology had no business producing. The answer is one of the strangest stories in human history, and it starts not underground, but in the sky. To understand how radical the discovery of iron was, you need to understand the world before it. For nearly 2 million years, human technology was defined by stone. Flint, obsidian, quartzite, these were the materials of survival. They could be chipped into edges sharp enough to cut meat and skin animals, but they were brittle. A stone axe could split wood, but one hard blow against bone and it shattered. Stone tools could not be reshaped once made. If the edge broke, the tool was finished. Then, roughly 5,000 years ago, something shifted. People in the Middle East and Eastern Mediterranean discovered how to smelt copper. This was itself a small miracle, realizing that certain greenish or blue-tinged rocks, when placed in a very hot fire, would surrender a soft, shining liquid metal that hardened into a shape you could choose. Copper could be hammered into thin sheets, could be cast in clay molds, could be sharpened and resharpened. But pure copper is soft. A copper blade bends rather than cuts when it meets something tough. And then metallurgists, though they would not have called themselves that, made a second discovery. If you mix copper with tin in roughly a 9-to-1 ratio, you get something harder and tougher than either metal alone. You get bronze. Bronze was the dominant material of civilization for nearly 2,000 years. Bronze swords, bronze shields, bronze plows, bronze chisels. The Bronze Age is the age of the first cities, the first writing, the first empires, and all of it ran on a metal alloy that needed 2 ingredients. And that was the problem. Copper was reasonably abundant, but tin is not. Tin deposits are scattered in a handful of specific places on Earth. Parts of what is now England, Central Europe, and Central Asia. For civilizations in Egypt, Mesopotamia, and the Aegean, obtaining tin required organizing long-distance trade networks across thousands of miles of land and sea. Ships carried tin ingots from Cornwall in Britain down through the Mediterranean. Overland caravans hauled tin from mines in Afghanistan toward the ancient cities of the Near East. These supply chains were fragile. A single war, a collapsed trade agreement, or a storm that sank a merchant fleet could leave an entire civilization without the raw material to make its most important tool. Egypt depended on trade. The Hittite Empire depended on trade. The Mycenaean palaces depended on trade. An element that would solve this problem was sitting in the soil beneath every single one of their feet. They just had no way of knowing it. Iron is the 4th most abundant element crust. It makes up more than 5% of everything beneath the ground we walk on. Mountains contain it. River sediments carry it. The reddish color of clay soil in many parts of the world comes from iron oxide, rust essentially mixed into the earth. There is virtually no place on the surface of Earth where iron or does not exist within a reasonable distance. And yet, for thousands of years of human civilization, people who had mastered bronze, built pyramids, written literature, and developed sophisticated legal codes could not do a single useful thing with iron. The reason is deceptively simple. Iron on Earth almost never appears as a metal. Unlike gold, which occurs in nature as shining nuggets in riverbeds, or copper, which sometimes appears as raw reddish metallic chunks in rock, iron is almost never found in its metallic form on the surface of the planet. The reason is chemistry. Iron has an extremely strong attraction to oxygen. Given any exposure to air and water over geological timescales, iron metal converts to iron oxide, what we recognize as rust. Every trace of naturally occurring metallic iron that ever existed on Earth's surface has long since been chemically transformed into dull reddish stone. What ancient people saw when they looked at iron or was not a hidden metal. They saw red rock, brown rock, heavy rock, rock that looked exactly like rock. Because as far as their experience could tell them, it was rock. There was one exception, and it came from space. Nickel-iron meteorites are fragments of the metallic cores of asteroids, bodies that broke apart during the early solar system. When these fragments survive the fall through Earth's atmosphere and land on the surface, they bring with them something that does not naturally exist on Earth. Native metallic iron, already in pure usable form, alloyed with a small percentage of nickel. These space rocks are extraordinary objects to encounter. They are far denser than ordinary stone. They are magnetic. When struck with a rock hammer, they do not chip or shatter, they dent. They have a metallic gleam when cut or polished. Everything about them is wrong for a rock. Ancient people who found meteorites recognized immediately that they were dealing with something unlike anything else on Earth, and they were right. In ancient Egypt, iron was given a specific hieroglyphic name that translates directly to metal from heaven or stone of heaven. This was not poetic language. Egyptian scribes were describing the only iron they had ever encountered, which genuinely had come from the sky. Ancient Sumerian texts used a term for iron that combined the signs for sky and external metal from outside, from beyond. Hittite ritual documents described iron as the black iron of the sky. Across cultures separated by thousands of miles, the same understanding emerged independently. This material was celestial, and because it came from beyond the sky, it was treated accordingly. The earliest iron objects in the archaeological record predate what we call the Iron Age by more than 1,500 years. These objects were not made from or pulled from the ground. They were hammered from meteorite fragments. In pre-dynastic Egypt, from cemetery burials dating to around 3,200 years before the Common Era, archaeologists recovered 9 small tube-shaped beads. When scientists analyzed these beads using modern chemical testing, they found very high concentrations of nickel, a chemical signature that is unmistakable evidence of meteoritic origin. These beads were hammered from a piece of iron that had fallen from space. In the tomb of the Egyptian pharaoh Tutankhamun, buried around 1,300 years before the Common Era, archaeologists found a dagger with an iron blade. For decades, debate surrounded this object. X-ray fluorescence analysis eventually provided the answer. The blade contained nearly 11% nickel and trace amounts of cobalt, a composition that matches closely with a known meteorite recovered near the Egyptian coast. The king of Egypt was buried with a blade made from a rock that had fallen from the sky. During the Bronze Age, this kind of iron was rarer than gold. Ancient Assyrian trade records from Anatolia show that iron commanded prices up to 40 times that of silver by weight. Iron rings and objects appear in palace inventories alongside jewelry. They were diplomatic gifts between kings. They were symbols of extraordinary status in an age when bronze was already the metal of power. This changes the way you have to think about iron's discovery. Before any human being figured out how to extract iron from the ground, iron was already known. It was touched, shaped, and treasured, but it was sky metal, or iron, the iron that would eventually remake the world, required something entirely different to unlock. It required a kind of fire that did not yet exist. Here is the thermodynamic fact that delayed the Iron Age by thousands of years. Copper melts at 1,085 degrees Celsius. Bronze melts at approximately 950 degrees Celsius, lower because alloying metals with tin reduces the melting point. The kilns and furnaces of the Bronze Age were built to hit these temperatures. Pottery kilns, designed to fire ceramic at high temperatures, routinely reached between 1,000 and 1,150 degrees Celsius. This was enough to liquefy copper and bronze, allowing them to be cast in molds, which is how bronze objects were made. Pure iron melts at 1,538 degrees Celsius. That gap, roughly 400 degrees between what Bronze Age furnaces could achieve and the temperature required to melt iron, is not a small engineering challenge. It is a completely different class of problem. The furnaces that could smelt copper and cast bronze, no matter how perfectly operated, were physically incapable of liquefying iron or